Hello, dear students. We are continuing our lessons, and today is new lecture by discipline Technological Foundations of Mechanical Engineering. And today is theme 5, Qualitative Characteristics of Products in Engineering. Write down to your notes the plan of our lecture. Item 1. Basic concepts and definitions of surface quality. Item 2. Influence of surface quality on the performance properties of the part. Item 3. Main factors influencing the surface quality. Item 4. Technological methods of improving the quality of surfaces of machine parts. And the last item, item 5, surface quality assessment methods. Please write down to you know the name of our lecture and the plan. Once more time, basic concepts and definitions of surface quality, influence of surface quality on the performance properties of the part, main factors influencing the surface quality, technological methods of improving the quality of surfaces of machine parts, and surface quality assessment methods. And now we start item 5.1, basic concepts and definitions of surface quality. The surface quality is characterized by roughness, waviness, and physical and mechanical properties of the surface layer. Surface roughness microgeometry is a set of irregularities with relatively small steps. It's irregularities with relatively small steps on the base length. Creating a surface relief of the part. Write down to your notes what is the surface roughness. Surface roughness, it's microgeometry, is a set of irregularities with relatively small steps on the base length, creating a surface relief of the part. Small steps, it's like in figure 5.1, small L, it's small step between irregularities. For example, between this and these irregularities, it's small step. It's roughness. It's roughness. You can see the roughness. And the next type, it's surface waviness. Waviness. Surface waveness is a set of periodically alternating irregularities with a relatively large pitch or step. Its irregularities with a relatively large pitch or steps, exceeding the base length taken when measuring. You can see irregularities with large steps. Big L, its parameter of surface waveness. Small l, its parameter of surface roughness. One more time, surface waveness is a set of periodically alternating irregularities with a relatively large steps or pitch, exceeding the base length taken when measuring roughness. On figure 5.1 shows a schematic representation of the roughness and waviness of the surface. Write down to your notes this scheme figure on the figure 5.1 with roughness and waviness. The description between the concepts of roughness and waviness is the ratio of the pitch or step to the height of the irregularities. For roughness, above the line, small l, under the line, h. Less than 50. For waveness, above the line big L, under the line h suffix b. H suffix b. This parameter for waveness from 50 to 1000. Please write down to your notes this scheme on the figure 5.1 with parameters. What is the surface roughness? What is surface waveness? And parameters for roughness and parameters for waveness. And now we are continue. The surface roughness is longitudinal and measured in the direction of the cutting speed vector, like in figure 5.2. A. And transverse measured in the feed direction, figure 5.2b. The following parameters are used to estimate surface roughness. The height of roughness, H1, H2, H3, and another H. And parameters B, B1, B2, B3. Parameter, the maximum roughness, R suffix maximum. And another parameters. Please write down to the scheme in figure 5.3. Its parameters are used to estimate surface roughness. The following parameters are used to estimate surface roughness, like in figure 5.3. A. The height of profile irregularities, R suffix Z, is the average distance between 5 peaks and cavities on the curve of surface irregularities. And we can calculate parameter r suffix z using the formula 5.1. It's the sum of five peaks and 5 cavities on the curve of surface irregularities and average volume of this sum. Its average distance between 5 peaks from I is equal 1 to 5 peaks, and 5 cavities from I is equal 1 to 5. It's 5 cavities, and average distance is 1 divided by 5. Write down to your notes formula 5.1. Equation to determine the height of profile irregularities. Height of profile irregularities. R suffix Z. B. Next parameter. The greatest height of irregularities R suffix maximum. You can see R suffix maximum on the scheme. It's the distance between the line of profile peaks and the line of cavities. Line of peaks and line of cavities. And this distance, it's R suffix maximum. It's R maximum, the greatest height of irregularities. The distance between the line of profile peaks and the line of profile cavities within the base length. What is the base length? Is this distance. Base length. Some millimeters. Next parameter. Clear this scheme and C. Arithmetic mean profile deviation R suffix A. Its arithmetic mean profile deviation R suffix A determined from the absolute values of the profile deviations H from the middle line. You can see middle line on the scheme. It's middle line. And you can see H suffix I. H, for example, H1, H2, H3, H4, H5, H6, H7, etc. And arithmetic means of these H's, it will be parameter R suffix A, arithmetic means profile deviation. It's H1 plus H2 plus etc. plus H suffix N and divide by N. It's not 5. It must be N. 5, it's only for parameter RZ. For parameter RA, we use N. Write down to your notes the formula 5.2 for arithmetic mean profile deviation, R suffix A. Parameter D. The average step of the asperities S suffix M and the average step of the asperities over the peaks S. You can see this parameter on the scheme. S suffix M it's a middle line, and you can see parameter S suffix M. It's step, average step. And S, for example, S suffix 1, it's distance between peaks. S2, distance between peaks. Or maybe this distance, it's distance between peaks too. It's S suffix 2, it will be S suffix 3, but average step, it's we use the formula to calculate average step on the peaks or asperities. Please write down to your notes formula 5.3. We use these formulas to calculate the step of roughness. The following parameters are used to estimate surface roughness. E, the relative reference length of the profile T suffix P. The ratio of the reference length of the profile to the base length in percent. We use the formula 5.4. In this formula, nu is the reference length of the profile equal to the sum of b suffix I. For example, b1, you can see b1, b2, b3, etc. And the sum of b, it will be parameter nu. Base length, it's L. You can see base length in the formula and on the scheme. A variation range of parameters. L from 0.01 to 25 millimeters. Base length can be from 0.01 to 25 millimeters. Parameters of roughness R suffix Z and R maximum can be from 0.25 microns or micrometers to 1,600 microns or micrometers. Next parameter, R suffix A. From 0.008 to 100 microns or micrometers. Step S suffix M and S from 0.002 to 12.5 micrometers or microns. T suffix P from 10 up to 19%. From 10 up to 90%. Write down to your notes variations range of parameters. Variation range of parameters. L, RZ, R maximum, RA, SM, S, and TP. The values of S suffix M and T suffix R characterize the shape of microroughness and determine the wear resistance and contact deformation of the connected parts. In rare cases, roughness is regulated by the direction of inequalities. The direction of the asperities affects the compatible contact of bonded surfaces. For example, for sliding surfaces, the coincidence of the direction of the machining strokes with the direction of sliding reduces wear. During cutting, plastic deformations and heating of the surface layer are observed, which change the state of the metal in this layer compared to the base metal. Physical and mechanical properties of the surface layer are characterized by its structure, rigidity, value, and sign of residual stress. During chemical thermal treatment, there is a change in the chemical composition of the surface layer of the workpiece. Have you questions about 5.1, item 5.1? Without questions. Okay. Item 5.2, influence of surface quality on the performance properties of the part. Wear resistance. The wear of the rubbing surfaces of parts in time obeys a certain dependence, like in figure 5.4. Write down to your notes figure 5.4. It's the change of wear during the time. The graph is characterized by three sections. The nature and intensity of wear is which differ significantly. The wear in the OA, first section, OA. You can see three sections: OA, first section, AB, second section, and BC, the third section. So, the wear in the OA area is intensively growing. This is where messages are processed. In section AB, second section, AB, wear is stabilized and conditions are created for more optimal operation of the connection. It's most optimal conditions for operation of the connection from A to B. Then there is an emergency wear of the surface. It's section BC. Third section BC, emergency wear. Write down to your notes this scheme in figure 5.4. Surface quality has a great influence of the performance properties of machine parts, its wear resistance, strength, corrosion resistance, quality of fixed fits, coefficient of friction, etc. The effects of the surface roughness of the mating parts on their wear is most pronounced during the running-in process. To reduce the primary wear of parts during running-in, it is necessary that the initial surface roughness be as close as possible to the roughness of the running part. The wear of non-run-in surfaces is affected by the shape and height of micro-roughness, the direction of asperities, waviness, macrogeometric characteristics, physical and mechanical properties of the material, lubrication conditions, and other factors. In the initial period, the unrunned surface is characterized by a profile with high peaks and deep cavities. So the load of the friction unit is distributed externally unevenly. In depressions, the specific load is small, and at the peaks of elementary irregularities, it reaches maximum values. Large local loads contribute to intensive wear. Intensive cutting and crushing of the peaks of irregularities, thus increasing the increase in wear. From this, we can conclude that parts with better surface quality, smoothness, have greater wear resistance. Since, in this case, the specific load in the joint is distributed more evenly. However, it should be noted that with a lower roughness, the wear resistance of the part increases only up to a certain optimal limit, after which decreases due to an increase in the adhesive component of friction. Strengths. The depressions of the microprofile of the surface of the part are peculiar stress concentrators which contribute to the formation of fatigue cracks to a large extent. The stress concentration coefficient of parts processed on metal cutting machines can reach values of from 2 to 2.5. It's stress concentration coefficient of parts. The presence of scratches from the cutting tool in places of height concentration of stress, grooves, etc. can become the cause of emergency breakdown of responsible parts operating under variable loads. Thus, in order to increase the fatigue stress of paths, high quality matting surfaces are provided, which is why they are processed. Corrosion strength. Corrosion strength. On a raw surface, substance that cause corrosion, decomposition products of oil, fuels, oxygen, etc., settle in cavities from where the removal is difficult. In addition, raw processing increases the area for active contact with air and aggressive substance that increase the corrosion process. Thus, smoother and cleanly processed surfaces are less prone to corrosion. The quality of fixed fits. The contact strength of fixed joints depends on the surface properties. The better of surface of the connected parts are processed, the greater the actual contact area, and therefore the more relatable the connection. The quality of the surfaces has a significant impact on the contact stiffness of the joints to be joined, reducing roughness, waviness, and macrogeometric shape distortions. It is possible to increase the butt area and consequently to increase the contact stiffness of the joint. Friction coefficient. Friction coefficient. In the interaction of raw surfaces, the coefficient of friction is of great importance. Parallel machine parts up to certain optimal values of R suffix A, excluding the predominance of adhesive properties in contact, have favorable conditions for reducing friction energy. However, it is not possible to say unequivocally about the influence of the geometric parameters of the surface on the coefficient of friction, since it depends on many conditions of friction: material type and properties of the lubricant, normal pressure, speed of relative movement, etc. The physical and chemical condition of the surface layer of the part also has a significant impact on operational properties. The surface smearing of the material and the final compressive stress increase the wear resistance and fatigue stress of the parts in most cases, but reduce the corrosion resistance. This is explained by the fact that the protective effect of the surface film on a highly deformed metal decreases. It is more easily destroyed by the action of internal stress. Next part of our lecture, item 5.3. Main factors influencing the surface quality. Main factors influences the surface quality. Surface roughness depends on. Surface roughness depends on the method and mode of processing. The method and mode of processing. The quality of the cutting tool used. The quality of the cutting tool used. The rigidity of the technological system. The rigidity of the technological system. The physical and mechanical properties of the material being processed. The type of coolant used. The vibrations of the technological system, etc. One more time. The physical and mechanical properties of the material being processed. The type of coolant used. The vibrations of the technological system. Please write down to your notes all these factors that influences the surface quality. Each processing method, points, grinding, etc., has its own range of the resultant surface roughness. In the table, 5.1 shows the surface roughness for various methods of processing: steel and gray cast iron, and compares the roughness parameters with the parameters of average economic accuracy. From a comparison of these parameters, one can see their relationship. The higher the accuracy of the obtained size, the lower the surface roughness. Then the higher the accuracy of the obtained size, then the lower of the surface roughness. You can see on your screens this slide with table 5.1. You can see processing method, for example, tuning or milling or drilling, grinding, etc. IT grade of accuracy and surface roughness with parameter R suffix A in micrometers or microns. And for tuning, preliminary or roughing tuning, IT grade it will be equal from 12 to 13. And roughness it will be equal 12.5 microns. For finishing tuning, IT grade of accuracy from 10 to 11, and roughness will be equal from 2.5 to 1.25 microns. For thin tuning or brilliant tuning, IT grade will be equal from 6 to 7. 6 IT grade or 7 IT grade. And surface roughness, it will be equal 0.63, 0.32 microns in this distance. For milling, preliminary milling or roughing milling, IT grade will be equal from 11 to 12, and surface roughness parameter R suffix A, it will be equal 12.5, like in tuning. For finishing milling, IT grade from 8 to 11, and parameter of roughness RA, it will be equal from 2.5 to 1.25. For thin or end milling cutters, IT grade will be equal from 6 to 7, to 6 IT grade or 7 IT grade. And surface roughness will be equal from 0.63 to 0.32. Drilling. For drilling, IT grade of accuracy will be equal or 11 or 12. 11 IT grade or 12 IT grade. And surface roughness will be equal from 6.3 to 2.5 microns. Countersinking. Preliminary countersinking, IT grade will be equal 12, and for finishing after roughening countersinking, its IT grade it will be equal 11. And roughness for preliminary from 2.5 to 12.5, and for finishing from 6.3 to 2.5. Next type of machining, hole broaching. IT grade will be equal from 7 to 8, and roughness will be equal from 1.25 to 0.63. For grinding, scrap and grinding, roughness it will be equal from 2.5 to 1.25. Preliminary grinding, IT grade, it will be equal from 8 to 10. And RA will be equal from 1.25 to 0.63. For finishing grinding, IT grade 7 or 8. 7 IT grade or 8 IT grade. And surface roughness will be equal 0.63 or 0.32. And thin grinding, IT grade 6 or IT grade 7, and roughness 0.32 to 0.08. Honing holes up to 8 millimeters in diameter. It will be IT grade 6 or IT grade 7, and roughness 0.32, 0.08. Please write down to your notes these tables with parameters after processing, parameters of surface after processing with different processing methods. When cutting workpieces with a blade tool, the surface roughness is largely dependent on the cutting speed and feeds. On figure 5.5, you can see figure on this slide. A shows the effect of cutting speed on surface roughness in micrometers, cutting speed in meters per minute. When tuning steel, Q1, it's for steel, and cast iron 2. After tuning, a steel billet at a cutting speed of about 20 meters per minute the greatest roughness is observed is associated with the phenomenon of active build-up formation on the cutting parts of the cutter. At cutting speed above 80 meters per minute, build-up age practically stops. In addition, at high cutting speeds, the depth of the plastically deformed layer is significantly reduced, which also reduces the surface roughness. So from 20 to 80 meters per minute of cutting speed, the surface roughness is decreased. It's for steel and for cast iron. Write down to your notes this figure 5.5, A and B. Depending surface roughness from cutting speed and depending surface roughness from feed. On figure 5.5b, shows the depends of the surface roughness on the feed when tuning a workpiece from steel 45 with a cutter with a top radius of 2.5 millimeters. It can be seen from the figure that a change in small feeds up to 0.2 millimeters per revolution somewhat affects the change in surface roughness. But when moving to the area to feet over 0.2 millimeters per revolution, the micro roughness of the machined surface increases. Micro roughness of surface increases more intensively. If increase the feet, we can see that surface roughness is increasing too, and most intensively after 0.2 millimeters per revolution of feet. With an increase in the depth of cut, the surface roughness does not increase very much and can be ignored in practice. Please write down to your notes figure 5.5b. The state of the cutting path of the tool has a significant effect on the surface roughness. The micro roughness of the cutting edge of the tool worsens the roughness of the machine surface. This is especially noticeable when processing with broaches, reamers of wide cutters. The dulling of the cutting tool leads to an increase in the roughness of the machine surface. When processing workpieces with an abrasive tool, the surface roughness decreases with a decrease in grainness and an increase in the rigidity of the grinding wheel, an increase in cutting speed, and a decrease in longitudinal and transverse feeds. When machining steel with a high carbon content, 0.05%, a cleaner surface is obtained than when machining low carbon steel. The use of cutting fluid coolant improves the roughness of the machined surface. Tool life is immediately increased. The effectiveness of the coolant in the operations of abrasive processing of products depends on many factors. The physical and chemical properties, the level of machinability of the workpiece material by abrasive tools, its size and shape, the required dimensions and quality of the part, in particular the quality of the restored surface layer of the material. Design parameters and condition of technological equipment, machine and technological equipment. Size and characteristics of the abrasive tool. The composition and physico-chemical properties of the coolant. The technology and technique of its application, etc. Please write down to your notes the factors of the effectiveness of the coolant in operations of abrasive processing. One should also take into account the universality of the coolant, the possibility of its rational use in various operations of machining parts by cutting, its operational and sanitary and hygienic properties, economic, environmental, and other indicators. When coolant is introduced into the processing zone, a weighting effect is produced, which facilitates the work of dispersion during cutting and friction. The effect of adsorption, plasticization, absorption, strength reduction of metal layers is caused. With the optimal combination of lubricating and cooling properties of the coolant, the head tiring wear of abrasive grains is reduced, and it is possible to avoid defects in the surface layers of parts made of corrosion-resistant steels. Due to the high level of vibrations of the technological system and their intensive increase in time, the coolant must have good damping properties, high dynamic viscosity. Thus, coolant should have. Optimal viscosity temperature properties for the ability to work at low ambient temperature to reduce wear of rubbing surfaces. Good lubricating properties to ensure reliable lubrication in all operating modes of the facility. Sufficient antioxidant resistance, which prevents a significant change in the chemical composition of the coolant during its operation. Good detergent properties in order to reduce the tendency to form deposits on heated metal surfaces and the lubrication system. High anti-corrosive properties, low foaming ability and emulsification, biostability. Of great importance is the purity of the coolant when reduced. Under real operating conditions, the coolant contains various contaminants that in a certain way affect its physical and chemical properties. The difficulty in ensuring the purity of working fluids is due to the lack of chemical justification for the use of cleaning systems in the abrasive processing of remanufactured car parts. Depending on the concentration and particle size of mechanical impurities in the coolant, defects such as scratches appear on the machine surfaces of parts, like in figure 5.6, which leads to an increase in the surface roughness parameter of parts in figure 5.7. You can see 5.6, figure 5.6, and 5.7. Write down to your notes these figures. Gradual increase in roughness parameter due to an increase in the probability of large particles of metals and abrasive getting into the coolant zone due to an increase in their number. Its concentration of mechanical impurities in grams per liter and the roughness parameter when concentration is increased, the roughness parameter increases too. Write down to your notes these two figures. Therefore, in order to avoid the influence of coolant contamination on obtaining the required quality of the surface of the restored parts of vehicles, it is necessary to thoroughly clean it, especially from the metal component of the pollutant. The rigidity of the technological system has a significant impact on the roughness and waviness of the surface. So, for example, at the point of a non-rigid shaft with installation in the centers, the greatest surface roughness is obtained approximately in the middle part along the length of the shaft. Insufficient rigidity of the system can cause vibration during cutting and, as a result, the formation of wavy surface. In figure 5.8, you can the hardness of surface. The physical and mechanical characteristics of the surface layer of parts and workpieces largely depend on the action of thermal and force factors during processing. The surface layer of the threaded steel billet consists of three zones. In figure 5.8, you can see first zone, second zone, and third zone. First zone, zones of pronounced deformation, a crystal lattice characterized by distortion, grain crushing, and increased hardness. It's first zone. Second zone, deformation zones, characterized by elongated grains and decrease in hardness compared to the first zone. And third zone, transition zone, zone of gradual transition to the structure of the base metal. Initial steel blanks or workpieces obtained by forging, casting, or rolling have a surface layer consisting of a non-carbonized zone and transition zone, zones with partial decarbonization. For example, workpieces or blanks obtained by hot stamping have a decarbonized layer in the range of 150 to 300 microns, and those obtained by free forging from 500 to 1000 microns. When processing steel blanks or workpieces by cutting, the depth of deformation extends up to 100 to 300 microns for cast iron blanks or workpieces. The depth of deformation propagations is insignificant, up to 15 micrometers. During mechanical processing of metals, the deformation of the surface layer is accompanied by hardening of this layer. with an increase in the depth of cut and feed, the depth of the hardness layer increases. So, for example, with rough tuning, the depth of slander is 200-500 microns. With fine tuning, from 25 to 30 microns. With grinding, 15 or 20 microns, and with very fine machining, from 1 to 2 microns. It's depth of hardened layer. And the last item of our lecture, 5.4, technological methods of improving the quality of surfaces of machine parts. In obtaining a high quality surface layer, an important role is played by finishing operations, of which grinding is the most common. The grinding process is characterized by the formation of high temperature in the processing zone, and as a result, the occurrence of tensile stress, which reduces the wear resistance of the part. To reduce residual tensile stress, it is necessary to reduce the intensity of head generation by reducing the depth of grinding, increasing the speed of the part, using softer wheels and copious cooling. We can use coolant. For example, the wear resistance of a part made of annealed U8 steel after fine grinding increases by 1.5 or 2 times compared to grinding under normal cutting conditions. At that point, the most wear resistance surface is obtained with high-speed cutting at low modes. Cutting speed 150-400 meters per minute. Cutting depths from 0.1 to 0.3 millimeters. Feed from 0.05 to 0.1 millimeters per revolution. So our time of lecture is finished. For today, we will continue on the next lesson. And I want to say you goodbye, have a nice day, and be safe. Goodbye.